Hi guys, if you don't know, I'm Daniel.
I'm Saksham.
And welcome to the Deep Learning and Neural Networks talk.
So today we're going to talk about neural networks and how it's used in artificial intelligence and why it's a good machine learning algorithm. Last week we spoke about linear regression. 2 weeks ago we spoke about linear regression with gradient descent. So today we're going to do a recap of linear regression and then talk about how that concept extends to neural networks. So firstly, this is just a quick review of linear regression. So we have essentially x theta equals y. So that's our main form. So x is our matrix of independent variables. Theta is our weights, the coefficient, the matrix of the coefficients of our independent variables, and y is our dependent variable. So what we're trying to predict. So if you were to draw it on a graph, you would have x, y, and we're trying to find values theta 1 and theta 2 such that we have x1 theta 1 plus 2 theta 2. So basically we want to find our two parameters theta 1 and theta 2 which best approximate the line of best fit for data points. So something like that. So in order to do that we looked at gradient descent 2 weeks ago. So essentially what we do is, so let's say we want to predict something y, let's call it, let's say height. We want to predict height based on x1 being age and say weight. So we have our matrix X of height, I'll just call that age, and weight. So this is an m by 2 matrix, where m is the number of data points here. So every dot here represents one data point. And so that's our X matrix, our matrix of independent variables. Then we have our matrix theta, which consists of the weights. So here we have theta 1, theta 2. This is a 2 by 1 matrix. And our output y will be a m by 2 matrix. So this is what we'll have to predict. So we want to solve for theta, our matrix of weight, because that's what we want to try to find out. In this case, so we want to find out theta 1 and theta 2. So what we can do, so if we have x theta equals y, we can't just divide both sides by x because they're matrices. So what we instead do is we multiply, we multiply by x transpose times x inverse y. Should be y.
Yeah, that's right.
So essentially we will get our matrix theta equals, because these cancel out, x transpose x.
So this is the least squares formulation of the...
Yes, so this is least squares. So what we're trying to do is the distance between each point, the square of the distance from the line to each data point, and then we sum that for every single data point. So we have, that's called our cost function, it's what we're trying to minimize. So that will be given by cost function of theta half. We half it, I forgot to say. The reason being is because it makes the calculus part easier when we're differentiating, so that would be y hat minus y squared. Yeah. So what that basically means is our cost function is so first we take the sum of the square of the distances of each data point from the line. So for example, this one is y hat I minus yi, and we square this distance, and then we sum that for every single data point, and then we just half it. I'm going to call this the half squared error. This would be the squared error. The mean squared error would be 1 on m, where m is the number of data points, but we'll just take half to make it simpler for us. So that's essentially linear regression, and from this we can determine our parameter theta using gradient descent, which we spoke about. So what we do with gradient descent is basically we update our parameter theta to its current value minus a learning rate called lambda. Let's call it lambda. Lambda times the total of the cost function.
The total derivative.
Total derivative. So this here is basically just it's a vector consisting of the partial derivatives of every variable in our cost function. So.
Oh, wait. Saksham.
Yeah. All right, the camera doesn't focus. I'll just do it here. Just do it small. So basically, the total derivative is a vector consisting of the partial derivatives with respect to theta 1, theta 2, and it goes on for as many independent variables you have. So here we have 2, so it just stops at theta 1 and theta 2. But if you have more independent variables which affect the outcome, then we take all of those coefficients of theta, coefficients of x, and we take the partial derivative of c with respect to that variable. And what you're basically doing here is you're updating theta with its current value minus some learning rate lambda. So I'll demonstrate this in 2 dimensions. It's a bit difficult in 3 dimensions because I can't draw in 3D. So, say we have a square quadrant. So this is our cost function. What we're trying to do is we're trying to minimize this value. So we start with some random weights here, and we want to go down. We want to find the value of theta for which this cost function is minimized. Now it doesn't always have to be like this. It could be, change that. Okay, yeah, so we have theta, its initial value, its new value is now equal to its previous value, minus some learning rate lambda times the total of the cost function, which is just this matrix here. So the way we choose lambda is it's defined in, we choose it from 0 to 1. Sorry, yeah, not 0. The reason we don't, actually, yeah, no, that's fine because it's not inclusive. The reason we don't choose 0 is because, well, obviously, if you set lambda to be 0, then theta is just theta, and that doesn't help because we want to update this. So we choose it in the range of 0 to 1, and that basically determines how quickly it goes down to its minimum value. And the reason we don't choose it too low is because it will take millions of iterations to go here. And if we choose it too high, what might happen is it will overshot the minimum value. It will go here if you choose it too high. And in some extreme cases, if you choose it high enough, it might even go off to infinity in the positive direction, and you don't want that because you're going further away from your minimum value. So what we do is we choose this learning rate, and we keep repeating this algorithm. The number of times you repeat that is beyond the scope of what we're doing here. But we repeat it enough so that it will converge to some value here. And when it does, then we have our matrix theta, which will be we will have some values of theta 1 and theta 2, which will best represent this line. So the coefficients will represent this line of best fit. And from that, we can select our independent variable. So based on the data we're given, we managed to create this line of best fit. So what do we want to use this for? Well, say we want to predict someone's height based on age and weight, which is not given in the data point. So you would input those parameters and you would get some output. By the way, I'm just drawing this in 2D here. If you notice, the cost function is a multivariable function. So I demonstrated it with a parabola here, but what it would actually look like is some plane. Well, not necessarily a plane.
So if you have 10 if you have 10 columns,
yeah,
then it'll be a 10-dimensional graph.
And obviously you can't draw that. We can draw up to 3 dimensions in real life. So it will look like some plane as a function of x and y. And we want to find the minimum value here. So to make this easier to represent, what we actually do, we use a contour graph. Y, x. So we basically, this isn't the exact representation, but this represents the gradient essentially, and we want to try and lower it. That's what we're doing basically, but in 2 dimensions here, for the purpose of easier demonstration. So that is linear regression, and what it's basically used to find is the line of best fit amongst a set of data points, and from that we can predict, given some independent variables, what the output will be. So now we're going to talk about another form of machine learning, which is more effective when you have a huge number of data points, which is why it's used in big data. So neural networks are basically a method of deep learning. So what we call deep learning is basically, it's an algorithm which is able to effectively deal with a large amount of data and a complex type of data set. For example, with linear regression, you saw we were trying to predict height from age and weight. Well, those can be numerical values, it's easy to do, but say you wanted to predict someone's face. If you wanted to create a program which scans someone's face, analyzes it, and then it tells you some characteristic about this person. Like this person's name is, nationality is, age is, and you can't just do that with linear regression because it will be very tedious. So for that we use what's called a neural network. So what a neural network is it's basically a structure of nodes formed in layers. So our first layer will be the input nodes, and then we will have some processing. This is called a hidden layer, and we will have some output. This will be the output node. So I'll just label that. This will be our input, our hidden layer. There are many hidden layers in a proper neural network, but here I'll just do one, and this is our output. The output only has one node here, but in reality it can have many nodes. Yep. So here we have 2 independent variables to predict one variable. But often you can have another one. For example, if you have 2 outputs. So we'll just do it with one here. So how it works is, so we put 2 inputs. So let's say we want to predict again, we use the same example. So we'll have age and weight. And our output will be some height. So how this works is, so we have this is our input layer, and it's connected to each node in the hidden layer. So every connection, we define a weight for it, a randomly assigned weight. We'll call this W1, W2, W3, and so on for every connection we have. Right. So what we do is, let's say we have an age 20 years old. and weight, say 70. So what we do is, we need to give this, this node a value. So what this will be is the sum of 20, which is our age, times weight I, from I equals 1 to 3, yeah?
It's just,
Oh, sorry.
it's just that.
Yeah.
This plus.
I'll just change this to 7.
Okay.
So this W2. Change that to W2. So basically this node, you can see every incoming connection into it. So we have one coming from W1 and one from W2. So the value here will be 20 times W1 plus, and this one's coming in, 70 times W2. I gave explicit examples, so I'll just use those. So this will be the value of this node, and as you can see, there's no other, we only have 2 input nodes, so there's no other connection for this particular node. And so that will be the value here. We repeat the same process here. As you can see, this one will also have 2 input nodes. So we have another weight, weight 3 coming into here, and some weight 4 assigned here. So this value will be 20 times weight 3, 20 times this, plus 70 times this one, weight 4, plus 70 times weight 4. And the same process applies here, and then it gets carried on to your output. So it will give some output. For example, height, it might say, it will obviously be wrong the first time because the weights we chose were randomly assigned. But let's say we know the outcome here. So let's say age 20, weight 70, we know that the height should be 170 centimeters here, in this case. For example, initially we won't get 170. Why? Because I chose the weights randomly and it's highly improbable. So we might get something wrong, like 120. So we know that this is not what we want, so we fix this using a process called back propagation. I forgot to speak about the activation functions, but we'll get more onto that later. So we basically it's a process of going back, where we update every weight, where we update the weights, and then keep going forward until our weight improves, so 135, then it will keep going until we finally get close to what we want. And I forgot to speak about the activation function, which is applied at every layer. You want to speak about the activation function?
Oh yeah, okay. Okay.
I'll just graph it here. Just rough that out.
Oh yeah, I'll draw that. Oh yeah, I forgot to tell you, guys, like you're probably thinking like with the cost function thing, and Saksham showed you how the cost function can be modeled as like this, right? So this is like a 2D representation of like a 2D valley, right? So if you think like this is the valley inside, you want to go inside, right? So if you say this is θ1, right, the parameter θ1, and this is θ2, right, this way, we're just labeling it as a cost function. So this is the cost function. What we want to do is pretend we start from here. And so how do we go to here, right? We can either increment θ1 by this way, right? We can go this way. Or we can go this way, right? This is old optimization. But in fact, what we can do is we can take the average, right? We can do that. And that's what gradient descent tries to do. We try to take the partial derivative, right? This is the partial derivative with respect to θ1, right? The cost function partial derivative with respect to θ1. This is the partial derivative with respect to θ2. And we just add them together, kind of, and we get this. And that's why we need to do 2 times. We need to differentiate with respect to every single parameter, because otherwise it will take forever. So we're just trying to average it out. And
each of these respectively will give you the total cost vector.
yes, correct. And this is the activation function. So what the activation function is remember before, a linear regression, right? A linear regression is also a neural network. The only difference is there's no activation function. Okay, so pretend this was age, and this is weight, and this is height, right? And this is parameter theta 1 and parameter theta 2. If you times them together, age theta 1 plus weight theta 2, you get the height. So this is a normal linear regression, right? And Saksham told you the formula and stuff. So what a neural network is instead of doing that, we apply another function over here. We provide another function like this. This is called the sigmoid activation, right? Sigmoid. This is the sigmoid activation function, and it squashes all the values from 0 to 1, right? So it never crosses the zero line. So all the values are between from 0 to 1, right? And we apply this function on linear regression. We apply on. And so the output, this height, not really, like it doesn't have to be height now, but this value is from 0 to 1. Right? And so why is this useful? Why do we need to squash it from 0 to 1? So if you know in a brain, how if you have neurons firing, sometimes neurons don't fire. So this kind of is like the probability of a neuron firing. It's from 0 to 1. If it's 1, that means the neuron fires, and so your memory, so your brain neurons keep going. If it's 0, then the neuron dies. And so this is like a model of like your brain.
The only difference being is that our brains don't backpropagate.
Yeah, they don't backpropagate. They only go forward.
Unfortunately.
Yeah. Okay. So let's take a one. So this is called a one-layer neural network, right? And we're just going to do. So this is your age plus your weight times the two parameters, right, is equal to the height. But remember, I told you there's an activation function, and the activation function is 1 over 1 plus e to the minus x, where e is the natural number e, 2.718, blah, right? And x is, yeah. So that's what it looks like. So, yeah.
That's the main one we use. There are also other options. Another common one is hyperbolic tan, so tan h.
Yep.
Basically anything that goes from, almost anything that goes from 0 to 1 as its range, you can use, but the most common one is sigmoid.
Yep, we're just going to, yeah.
And that's the one we're going to use.
Yep, we're just going to use the sigmoid activation function. So it's just a probability from 0 to 1. So remember in linear regression, right? Remember linear regression was height is equal to age times theta 1 plus theta 2, weight times theta 2, yeah, this. But then remember what neural networks does is we apply an activation function on it. Right? So that's what height equals to. Height is equal to the activation function applied on linear regression. And this can also be written, because remember this, right? We can just write this as 1 plus e minus a theta 1 minus w theta 2. Right? We just replace the x with all of this. And this is what it becomes. And remember, if you remember from before, this can also be, the prediction is y hat. Right? Y hat, the hat means prediction. If there's no hat, that means it's a true value. Right? So this is equal to y hat. Okay? So just remember that. Okay, so with this, right, we have this now. We have y hat. But remember, what is the cost function? The cost function is 1/2, right, the sum of all the y's, the prediction minus your y, your true y. This is your true y, this is your prediction, and you square it, right? So remember, why do we square it? Because we want to penalize the bigger differences. The bigger the difference between the true value and the fake value, we want to make it bigger. So that's why we square it. Right, so this is the cost function. And remember, the gradient descent algorithm says that the theta, the parameters, gets updated by the old theta, right, minus the learning rate, which is from 0.01 to 1, times the total derivative of the cost function. Right, and this upside down triangle means total derivative, if you remember from before. And this thing is just, as Saksham said, remember the two partials, right, the two partial derivatives, we talked about it. We average it out, and that's what it looks like. Right, so we need to find this. Right, so just remember this. All right. Right, that's your y hat. Okay, now we need to find it. Okay, so remember the neural network looks like this. Right, this the activation function is here. Right, your y hat is your prediction, and here is the parameters, and here is just your x values. Right, this is what it looks like. Right, if you project it on like here. Right, and here I'm going to put the cost function here. So remember, if you go forwards, you get y hat, and if you go forwards, we just do x times theta, apply the activation function, and that is equal to y hat. Right, but remember what back propagation does. Right, is literally go backwards. So we start from here, we literally go backwards, and then we go here, and then we go forwards again, and then we go backwards. And the amount of times you want to do this, it depends on how many times you want to train it, but this is called the number of epochs. This is how many times you want to train the system to learn. We want to learn this, right? And as many times as you go backwards, it will keep updating, and your new prediction will keep changing until it becomes exactly equal to this, right? This is what we want. We want the prediction to be exactly equal to y. And so what this means is that a neural network is a universal function approximator. Whatever function you give it to it, it will try to approximate it with another function. Oh, anyways. So with that, so remember, back propagation, you start from the cost function, right? You go onto y, and then you go onto theta, right? And then you go back. So with this logic, let's write it out. Remember, the total derivative is this, right? That's the notation. So what we do, okay, so watch carefully. Okay, this, remember, we want to differentiate this with respect to the parameters, right? This is what we need to find. Well, just look, if you go from here, right, just write it. The c is over here, the cost function, right, over y hat. Right? And then y hat over theta.
Yeah, this is just the chain rule.
Yeah.
If you remember from calculus.
And if you see, like, if we do that using just logic, right, look what happens. We can cancel these out, right, and it'll be exactly the same as this. But we don't want to cancel it out, because if you cancel it out, we can't work out the total derivative. So just remember, cost function over the prediction, and then the prediction over the parameters. And this is your chain rule. Okay, so remember, do not cross this out, okay? Because we're going to use this. Okay, so let's do the first one first, okay? So the total derivative of the cost function with respect to y hat. Now remember, y hat is this. And the cost function is 1/2 the total sum of y hat minus y, right, squared. This is your cost function. But remember, we don't need to use this temporarily, because this is just respect to y hat, which means we don't need to care about this. This is already here. So we don't need to plug this back in. So in fact, this is the same as saying the total derivative of just this, right? But remember, this is stochastic gradient descent. From before, we told you that stochastic gradient descent only looks at one data point. It only looks at one row. And if that happens, that means we don't need to add it all up. So we don't need to put the sum sign, because that's not stochastic gradient descent. We want to do it for each row, so we delete the sum sign, but we need to put the i's. So the i's mean y1, y2, y3, y4. So for each y, and because we do this, we have to change this, because we're now not finding the total derivatives. Okay, that's what it looks like. And to differentiate this, how do we differentiate this? Because there's a y, we just want y hat, right? We bring the power down, so 2 times half, which is 1, and then we times the differential of the inside, which is 1. So that is just y hat minus y. Okay? So that's the total. So we found that this part is that. But now we need to find this part. Okay, so this part will be a bit more complicated, but so listen carefully. Okay, so this. What is the total derivative respect to y hat? But remember, we have to do it with each, sorry, not that one, that one.
It's each way, theta 1, theta 2.
Yeah. Remember, how many thetas are there? We have theta 1 and theta 2, which means we have to do the first one first. Right? With respect to theta 1. And what is this equal to? So the derivative of theta 1, right, is the same as saying the derivative with respect to theta 1 of that. Okay, so we just copy all of this and put it over here. So 1 over 1 plus e minus, right, we get this. And remember, if you remember from high school, if you did maths in high school, or you watched our other videos, the derivative of a quotient is differential of the top times the differential of the top times the bottom minus differential of the bottom times the top all over the bottom squared, right, if you remember. So let's do that. The differential of the top is 0 times the bottom is 0, so 0 minus differential of the bottom. Remember, if it's exponential, the differential of the exponential is just the same as itself times the differential of the top, right, and the differential of the top is this, right, because theta 1 is just here. But remember, there's a minus sign. So minus times minus a1 is positive. Oh, yeah, not minus. Yeah. Right? So this, and then we remember we write the same. Remember the differential of the exponential is the same as itself, so we write it again. Right? All over the bottom square. Right? We get this. So that is a differential of this, right? But if you remember, if you see this more clearly, right, this, right, the bottom part, this 1 plus e to the blah square, kind of looks like this. The only difference is this is exactly this square. Right, so what we can do is we can write this as ae minus a1 minus, right, all of this, all over the bottom, right, all over this, 1 over this, right? Because if you do 1 over this, if you do 1 over all of this, it just becomes 1 plus e. Right? So we do 1 over it. But remember, there's a square there, so we have to square everything. Right? And remember, if it's 1 over something, we can change this and put it over here. Right? So what we have found is that this is equal to ae minus a, right, times this. And that's what we have found. Right? And remember, for the second one is going to be exactly the same, just this will be changed to w. Okay? So, okay, anyways, so remember, this is a matrix. Remember this is supposed to look like this. Right? Remember we told you that's the 2 directions we have to go. But don't forget, the total cost function is and remember what's this? This was just y hat minus y, right? And this is that. Right? So this will just look like this. So all of this blah. Right? That's what it will look like. So we get this, we times it by that. And that is your total cost function. And then after you do some smart manipulations and stuff, remember we told you like we can factorize this out, right? This can be factorized out because this is exactly the same. We find that if you factorize it out, it becomes right, if you factorize that out, it becomes this. But because you did that, we have to transpose it. You just watch the other video and you will know what I'm talking about. And then remember, this is the same as x, right? This is the same as x of I, right? And so we just put the x, we replace it with x. And then all transpose it.
The rule used here is just if you have 2 matrices, AB transpose is B transpose A.
Yeah.
So that's what we use here.
And what the transpose does is if it looks like, if there's a column row like 1, 2, 3, right? If we apply the transpose, it will look like 1, 2, 3. And that's what the transpose like just does. And if you do this, if you expand it out using Saksham's rule, that means this part goes in front, right? And the rest goes over here. And so this is your cost function. Okay? And remember, what is this? This is just x times theta. So we can replace that with x times theta. Oh, sorry, minus. Don't forget about the minus. So, yeah, so we found out we have just derived a one-layer neural network, the formula for it, right? And that is, the theta gets updated by theta minus the learning rate times x of I t y hat squared e to the minus x theta. Right, and that is your one-layer neural network formula. Sorry, it's very, yeah. But if you have multi-layers, it will be even more complicated. But we're only going to do one. Okay, so now we're going to code this in Python from scratch.
Yeah, just to re-emphasize, this is just one layer. So as we said earlier, if we have two inputs and an output, this is just a formula which deals with this. In reality, there will be like thousands of these and like millions of connections going everywhere. And you can try doing the math on that and see how it works out. Okay, let's code this in Python now.
So this is linear regression. So this is the revision from 2 weeks ago.
Put them all back. Oops, sorry. Oh no. How to make it bigger? It's very big.
It's a free. I don't know this. I already did it.
Oh, okay. So just remember. So the example we're going to do is we're going to predict if I'm going to be happy or not happy if I eat apples or oranges. Okay. So I think is it apple? Oh, it doesn't matter. Okay, so apples, right? Apples and oranges. Okay, and the condition is if I eat more oranges than apples, I'm happy. So if oranges is more than apples, I'm happy, right? If anything else, I'm not happy. Oh, if it equals to, because that equals. But if oranges is more than apples, I'm happy. And we want a neural network to train to realize this pattern, right? And so in math terms, we could just draw a straight line. Any dot you point over here means I'm happy. So everything over here, I'm just going to put 0. Oh, sorry. Happy means 1. So this will be all 1s, right? And anything over here, I'm not happy, which is 0. And so we made some fake data. So this is your fake data. So this is your apples and this is your oranges, right? So if I eat 4 apples, 1 orange. Oh wait, I think it's the other way around. Anyways, yeah, it doesn't matter. So 8, 2. So this is what it means. And to code it in. So remember to open your Jupyter notebooks or Kaggle if you know how to open it. Like you should be able to open it by now.
Yeah. So just for those of you using Kaggle kernels, I'll just open this. Just go to kernels. Create a new kernel notebook, and we'll just search for Titanic.
Oh wait, that's the one. Just do the competition. To add. No. It doesn't work. It doesn't. You don't need to add.
We don't need that.
Okay, yeah.
And then to add more lines for interpretation, we'll just click the plus. There's a plus here. Okay.
Okay.
Yeah, and now import.
Oh, okay. The constant account.
Okay.
Yeah. So remember, the libraries we're going to use in Python, the most important libraries are Numpy. Oh, no, not important. So remember, we're not going to reference by NP, so this is more easier. From Numpy, import everything. Right? The while, this star means everything. So we want to import everything. No. Right? We just do that. We only need to use one library to code our neural network. Okay? So remember, we want to make some fake data to see what this relationship is. Okay? So let's just make this up. So oranges and apples. Okay? Let's say that I eat 10 oranges, 0 apples. 5, 3, 10, 20, 5, and
more.
yeah, 5 and 8. Okay, let's just do that. Okay, so if you do happy, remember the condition must be oranges must be greater than apples. So I'm not. So this is good, so I'm happy. This is good, so I'm happy. This is not good, so I'm not happy. And this is not good, I'm not happy. Okay, so we just put this data in. Okay, so how do we do that?
We'll call this matrix X, right? Left
Oh, yeah. So
X is matrix. Use 10. Use this random.
yeah, that's just that.
10, 5.
Yeah, that's right. No. Right, so in Numpy, to make a matrix, you have to, so these are all the columns, and these are all the rows. What? What did you do?
Matrix.
No, wait. No, oh. No, that's not, no, that's not how you do it. No, you have to do this. You have to put 2 brackets.
Oh, so that.
No, another 3.
You put the X like that.
Right, and you just print it out. Right, that's what it looks like. But remember, we want to transpose it. Right, we don't want that. We want it to look like this. So how do we do the transpose? Yeah, so we just put dot T, and dot T is your transpose. No, big T. And that's what it looks like. But now we also need the Y variables, right? 1, 1, 0, 0. So we put it in. Y is equal to matrix 0, 1, 1, 0, 0. Yep.
And we transpose that as well.
Yep. Print it out, check. Right, that's what it looks like. So that's good. Okay, so make new cells. Let's do the grading descent algorithm. Oh. Just make like tons of cells. No, there isn't. Okay, go. Okay, go down. That's it, that's enough. Okay, so remember we have 2 parameters, right? Parameter theta1 and parameter theta2. We want to add it together. Theta1 times orange. Oh, okay. Theta1 times orange plus theta2 times apples. Apply the activation function and we get happiness. Remember the activation function squashes everything from 0 to 1. So that's why we can use the sigmoid. Remember the sigmoid looks like 1 plus e. Remember, that's the activation function.
Create our weight matrix as well.
Oh yeah, so remember, before you start anything, we have to initialize the weights. So let's just make the weights 0.1 and 0.1. You can do whatever you like. You can do negative 0.10, like 0.1 and 10 or 1,000. It doesn't really matter.
We just started with 0.1, 0.1.
Yeah.
Like that.
Yeah. Okay. So we initialize. So our beginning variables is that, right? So okay. So remember, just write this formula down. Okay. So this is the same as saying the activation function applied on x theta. Okay. So let's just write that. So the activation function is 1 over, remember, 1 plus,
Define it first.
oh, it doesn't matter, right, exponential of minus times x. Remember the x we already have? X was this, times theta, the current theta. Right, and we get this, right, we get 0.7, 0.6, 0.9, 0.78. Right, but we want 1100. So how do we update theta to get that? So that's what we need to do. So if you remember, what is the cost function? The cost function is the prediction minus the real y's, right? Or square.
And
Oh wait, you have to do square. Yeah. So you apply the square, right? And halve it. Remember the cost function? This is the cost function. We get this, right? But we want to update the cost function. So how do we do that? So to update the cost function, we have to. So for one iteration, remember what is this formula? This formula says theta gets updated by minus the learning rate times the transpose. So you literally just put this formula in. Okay, so we derived it already. Just shove it all in. And what is that? So theta, right, minus the learning rate. Let's just choose the learning rate to be 0.05. Right, remember it's from 0.01 to 1 times x transpose. Remember, stochastic gradient descent, there's the I there, right? There's an I. The I means for each training example. So remember, the first row. So how do we do this? The first row means it's 0, right? In programming, when you reference the first row, you start from 0. Okay? So that's the first row, right? Transpose. Okay? Remember there's a transpose? Times y hat, so this is your prediction, and the prediction is all of this.
just assign it a variable.
Oh yeah.
Instead of using it.
Y hat. Okay, so times y hat squared. Oh wait, we can just do square. Oh wait, no. Yeah, square. Right, times y hat squared, right, and then times the exponential of minus x, right, no transpose this time, times theta. Oh, did I do something wrong? Oh, yeah, wrong shape, sorry. Okay, so theta looks like, theta looks like that, that's good. Right, so this is how you can do error checking in Python. Right, you just do stuff like this, right, that looks fine. And then what happens if you times y hat? Let's see what happens. Oh, see, that's an error, so that's not good. So let's check what y hat looks like. So y hat looks like a 4 by 4. Right, see, what's the error we did? It's for each example, so we can't just do that. It's in fact this, right? Remember, y of I. So we have to change this and do, this is how you do error checking. Right, and we get this. Okay? So after we literally just plug in the whole formula in, we get that theta must be updated by that. Okay? So, theta is equal to that. Okay, because we want to update the thetas. No, I already minus it. Okay? Right, and so theta, the new theta looks like that. What was the old theta? The old theta we did was 0.1, I think.
0.5 and 0.1 and 0.1.
Yeah, some number, right? And so we updated it. So this is the update. And to update for each one, we use a for loop. So we keep updating. So for the number of updates, for n means number of updates, in range, 1,000, let's just do 1,000 updates. Right, I'm just going to copy and paste because it's going to be too long. Where is it here? Anyways. You can check this code later. Wait, did I do? Oh, learning rate. The learning rate is 0.05. Oh, that's good. Huh? Oh, the grade. Oh, I didn't do the gradient. No, wait, did I do something wrong? Oh, wait, no, I have to copy.
You forgot the gradient.
Oh, it's, you have to copy all of this. I just used this. Okay, because we don't have enough time, I'm just going to copy and just show you. So you can just look at this yourself. So this is the same data. This is a different data set, but it's the same logic. Okay. So yeah. So I initialize it to be from 0.1 and 0.1. Right. If you do one iteration. So this is y hat. Right. So it's not good, and we want to update it. And we updated the gradient. More cells. And this is your cost, so this is your how many iterations. So you can look that up. And if you run it, yeah, okay, so we ran it, okay? And for the plotting library, so let's see what theta looks like. Right, the new theta is negative 0.8 and 0.7. And let's see what y hat is. And y hat looks like that, right? 0, 0, 0, 0.9 or 1, 1, 1. And that's what we need, right? Before, if you check, we just want 0, 0, 0, 1, 1, 1. And in fact, we get, after 1,000 iterations, we get 0, 0, 0, 1, 1, 1 after you round it off. Okay, so let's plot the, so if you do want, the plotting library in Python is matplotlib. Right, using this is your plotting library. So let's just plot the cost function. Let's see what the cost function looks like. Right, as you can see, the cost function is becoming 0. So let's change the number of epochs to like 2,000. Let's see what the cost function looks like. So it's running, running, running. As you can see, the cost function is becoming closer and closer to 0, 0.010. And so we have, yeah, and so we have made a neural network from scratch. And if you want to predict, right, if you want to predict the new thing, so let's say that the data doesn't, so let's say I want to find if I'm happy or not happy if I have 5 oranges and 5 apples, right? And I can see that's around 0.4. It's not that good, but it's good enough. If I have 0 oranges, if I have 10 apples and 0 oranges, I'm very unhappy. So the number is 0, right? And if I have 10 oranges, I'm very happy. So now we have learned how to code a neural network from scratch. Check the code out and copy and paste, and just play around. We just use the formula. So we literally just use the formula we derived. And yeah, that's all. I'll post the links for the code on Facebook. Yeah, thanks.